Thank you for inviting me. So I'm going to talk about regulatory decision making and how we can combine the so-called deterministic approach, which is a misnomer, the conservative approach with the risk information. Now, the concept of risk. These are the three questions we are answering in risk assessment. You have a technological system, you want to know what can go wrong, what kind of off-normal situations may develop. And we are looking at nuclear power plants at thousands of accident sequences as opposed to the standard regulatory approach. But then importantly, we're also asking how likely are these accidents and what are their consequences, okay? These questions were not asked before, or they were answered in a different way, as we'll talk about it. So this so-called risk triplet now is used by many industries, not just the nuclear guys, aerospace, the Coast Guard is using it. So one concept that is very important here is the concept of residual risk. And I've had many opportunities to visit Japan, for example, and such a concept is very foreign there. They don't think in terms of risk or probabilities or uncertainty. So it's important to realize that all activities and technological systems pose a residual risk. And here I have some examples. They're a little dated, but annual residual risk, occupational risk is about 40 deaths per 100,000 people. Heart disease is the #1 killer when it comes to illness. These are important because the safety goals of the Nuclear Regulatory Commission were based on these. Okay? The Commission said nuclear power should not contribute significantly to the existing risks. So, and in fact, the Commission said we want the quantitative health objectives of the nuclear industry to be 1,000th of these. So you take whatever rate you have here, you divide by 1,000, and you get the NRC's goals. And of course, the residual risk, we used to call it acceptable risk. The counter argument is that no risk is acceptable. You tolerate a residual risk because you derive benefits from that activity, okay? And nuclear power, of course, the benefit is electricity. Typically, I said that we have quantitative health objectives in terms of cancers and so on, but in day-to-day operations, the industry and the NRC are using these two metrics. The core damage frequency, which is a surrogate for latent cancers, is self-explanatory. The frequency per reactor year of accidents that cause severe fuel damage. And the large early release frequency is, the definitions are a little fuzzy, by the way. They are not precise, but there is a reason for that. So basically, LRF is the frequency per reactor year of a rapid, unmitigated release of fission products from the containment to the environment that occurs before effective implementation of off-site emergency response and so on. So it's really a fuzzy definition, but it works very well in practice. And the reason is that the risk assessments and all that, they discretize everything. So, you know, whether you're here or there in that cell, it doesn't really matter. Now, here is an overall view of the PRA model. When you're dealing only with a plant, in other words, you're trying to develop accident sequences that lead to core damage, we call that a level 1 PRA. The results of this analysis are accident sequences that lead to damage of the fuel. And you see the goal up here. I mentioned the two metrics we use, core damage frequency and LERF. The goal is once every 10,000 reactor years. The frequency of damage in the fuel should be less than that. It's important to emphasize that goal has a meaning in regulatory space, as opposed to criteria. A criterion means you're not supposed to violate it. If you do, you will be punished one way or another. A goal is something you're striving to achieve. So even if you exceed the goal, the utility is expected to try to bring the number down, but there will not be regulatory action just because you exceeded the goal. There's a fundamental difference between a goal and a criterion. Once you have these accident sequences, and you have already damaged the fuel, you enter the level 2, which is the containment model. And the science is different here. In the plant model, you have a lot of Boolean algebra. This pump works, it doesn't work, the valve works, it doesn't work, and you create the sequences. Here you have a lot of physical and chemical phenomena. We have never seen large-scale core melts, so we really don't know if you have molten fuel in the containment, what happens. But there have been a lot of experiments at national laboratories. So, as I say, the science is different. And the output of the containment model is the release of radioactivity to the environment. And we have the second goal, 10 to the minus 5 per reactor year. Once you release radioactivity, then you worry about the consequences, public health effects. And that's where the Commission put the goals, the quantitative health objectives, 1,000 of the rate of accidents and the rate of cancers. The reason why we needed these subsidiary goals is this arrow here. The uncertainties in the estimates of the frequency of these accidents increase as you move from left to right. Okay? Here, we feel now that more or less we understand the uncertainties. Once you move in here, we've never seen that, the uncertainties go up. And they are compounded with these uncertainties. And when you get here, then you have dose-response relationship, uncertainties, and so on. So it's not practical to work with these objectives, because what do I mean by that? Suppose a utility wants to change the testing frequency of a group of pumps. Typically, you have the baseline risk assessment the way things are now, then you do a risk assessment with a new testing frequency, and you look at the difference. If this were the metric you're using, there is no difference. It disappears in the uncertainty. You have such large uncertainties that you can't make a decision. That's why we have these two. And frankly, the industry really pays more attention to this one, because they feel that we are dealing with equipment that we understand their failure rates and so on. Once you enter the containment model, a lot of it is unproven science. But anyway, these two are used for routine decision making. Just to give you an idea of what results risk assessment gives you for a nuclear plant, this was in the Northeast, and this pie chart shows you the percentages in terms of the initiator of the accident. Okay? So when it says internal events, 54% of the core damage frequency, these are LOCAS, loss of coolant accidents, and transients. Earthquakes contribute 21%, internal fire 9%, flood 5%, and weather 10%. Okay? So this is one of the results that a PRA produces. It looks at the whole plant, not just some pre-specified accident sequences. And you have the whole set of accident sequences available for decision making. Now, I will contrast this with the traditional approach to regulation, which is still in place. It has been modified a little bit, but it's still in place. And it was created back in the 60s and early 70s, by and large, when the utilities started building nuclear power plants. At that time, the uncertainty was unquantified. People were trying very hard to make the accidents very unlikely without having the benefit of quantification, how likely they were. So they came up with an idea which I think was very, very clever, the principle of defense in depth. Safety margins is part of defense in depth. So much later, everybody knew what defense in depth was supposed to do, but there was no definition of defense in depth, and until 1999, 20 years plus after they started implementing it, the Commission issued a white paper where they say that it's a safety philosophy that employs successive compensatory measures to prevent accidents or mitigate damage if a malfunction or an accident occurs. So the use of multiple barriers is the fundamental principle of defense in depth. And it's still the reigning principle, okay? Even though it was defeated in Fukushima. So here are the major elements of defense in depth. You try very hard to make sure that accidents will not happen. So you have a number of safety systems to provide cooling if, in fact, you're losing coolant. And there is a multiplicity of these. You never rely on a single system. And a single system never has one train. You always have redundancy within each of these. But if all of these fail, then you have the containment dome that is supposed to contain the radioactive materials that have been released from the reactor core. But then, you see, that's the idea of defense in depth. Another way of thinking about it is, yes, we are doing the best we can, but what if we are wrong? Okay? So, even though we have a very strong containment and multiple safety systems, we do everything we can to prevent accidents. At this point, we say, what if we are wrong? And we require accident management. Okay, there are guidelines how to do that and all that. And the ultimate defense in depth is the emergency plans and the siting of the reactor, of course, at the beginning. So, at a high level, this is defense in depth. But then in each box, you also apply defense in depth. That's why the plans are so expensive. An important element of the traditional approach is, again, the concept of design basis accidents. And the definition is here. It's a postulated accident, in other words, regardless of its frequency. It's a postulated accident that a facility is designed and built to withstand without exceeding the off-site exposure guidelines of the NRCs. They are very stylized and very unlikely. The most severe DBA is the large loss of coolant accident, where you take the largest pipe in the plant through which coolant circulates, and you assume it breaks in a guillotine manner, and you lose coolant from both sides. At the same time, you have to assume you don't have off-site electric power, and at the same time, you have a single failure in a safety system, in a critical safety system. Okay? That's what I mean by stylized. The accident is dictated by the regulator. As an example, we've had now several thousand reactor years of experience with piping. We have never seen a large pipe break anywhere in the world. And in fact, there was some serious research done at Lawrence Livermore National Laboratory years ago, where the saying leak before break was established. In other words, such a large pipe will never break. It leaks first, which means, of course, that the plant personnel know that it's leaking and they will take appropriate action. Still, the large break LOCA is a major design basis accident. There have been some efforts to relax the requirements, because it's not just the accident itself, it affects many other things. For example, in the containment, there is the containment spray system that sprays water into the containment if there is a release of radioactivity. And because of this large break LOCA DBA, the containment spray system is automatic. The operators cannot intervene. And what do you know? There have been 2 or 3 inadvertent actuations of the containment spray system, creating a mess in the containment, costing a lot of money to the utility and so on. But things are the way they are. Now, how many DBAs are there? Very few. 15, 16, 17. That is again to be compared with the thousands of sequences that a PRA generates. Okay? A good thing about the DBAs is this. In the nuclear business, nuclear safety, what is it that worries the responsible people the most? That something will happen that we had not thought of. If we can think of what may happen, we make sure that it will never happen. The problem is the so-called unknown unknowns. So by having these stylized design basis accidents, the idea was that they would protect us. And that's, of course, the idea behind defense in depth, too. If something happens that is unexpected here, at least I have the containment to protect me. Okay? So these unknown unknowns are really a major concern of when I was on the commission. I was thinking about it all the time. What can happen? What happened in Japan, unfortunately, was not an unknown unknown. It was a known unknown. So, anyway, the traditional approach has served us very well. We've had 3 Mile Island and so on, but basically the industry is safe. But the first bullet here is very important. There is no guidance as to how much defense in depth is sufficient. It's a great principle, but what do? I mean, I go back here and say, what if I'm wrong? Maybe I should build a second containment. How about a third containment? And pretty soon, you shut down the industry because building a plant is very expensive. So how much defense in depth is sufficient? We don't know. Now, as I said, in the early days, they didn't have the benefit of quantification, but they established defense in depth and the other regulatory criteria to keep the accident frequencies very low. One was the single failure criterion. So if you have one of the safety systems and you postulate a single hardware failure, the system should not fail. Another way of saying we want it to be redundant. So typically the cooling systems have 2 trains, sometimes 3. So if one train fails, you have the other one. And I already said that the design basis accidents are stylized. And for example, people became aware of the fact that operators can make mistakes. So you're trying to impose requirements like for the first 30 minutes of the accidents, we don't want the operators to do anything. They do not reflect operating experience. I gave you already the example of large pipes. They just don't fail. And yet, you want a license, you have to show to the staff, to the NRC staff, that if there is a guillotine break of the largest pipe, and loss of offsite power, and the single failure, you can still tolerate it. Another interesting point is the last one, that once the industry started doing PRAs, there was a variability in risk. And you say, wait a minute now, why should the core damage frequency at Seabrook be different from the core damage frequency at Quad Cities? They were licensed under the same regulations because the risk is very plant specific, that's why. So here's a plot of the best estimate of core damage frequency across the fleet, and we have here the fraction of plants that have this particular core damage frequency, and you see it goes from a little bit over 10 to the minus 4 per year all the way down to 4 or 5, 10 to the minus 6. And all of these plants were licensed in the same regulatory system. So the question is why? Why do I have this variability? And as I say, plant specific. Now, the first PRA came out in 1975. It's known as WASH 1400 or the Rasmussen report. It's now history, but what I have here is examples of how misconceptions were changed after the PRAs were done. So, the major design basis accident was the large LOCA. The PRA comes out and says, no, it's small loss of coolant accidents that dominate the risk. You don't have to assume that the largest pipe breaks in a guillotine fashion. And the core damage frequency, they couldn't quantify it, but if you asked people at the time, they would tell you, no, it's extremely low, it's probably once every 100 million years and so on. And the study comes up and says, no, it's actually much higher than that. And this, at that time, because of some studies that had been done at Brookhaven National Laboratory, the infamous WASH 740 that said that if there is a serious accident at Indian Point, everybody in New York City would die, just about everybody. So people felt at the time that the consequences would be disastrous. And here comes the PRA, no, even if the core is damaged and there is release of radioactivity to the environment, the consequences are significantly smaller than what people thought. And then it was the first time that human actions were declared as important contributors to risk. Because in the 50s and 60s and 70s, the designers were engineers. They were very good at thermohydraulics, transient analysis, and so on. Worrying about human error was considered a soft science that had no place in a hard science like nuclear engineering. And then the first PRA shows that human errors are important. And if you look at the accidents around the world, including Fukushima, it was never the technology, it was management that created the conditions for the accident, okay? It took the nuclear industry years to accept that human actions are important. Okay, regulatory decision making now. It should be based on the best current state of knowledge. That's a truism, we all agree to that. And how is the current state of knowledge regarding nuclear power formed? Well, you have to know the design, the operation, and the regulations. The reason why I have this slide is because there was strong resistance by the traditional people to risk assessment. We are replacing experiments by voting, by human actions, you know, a lot of stupid things actually, in retrospect. It's a little bit understandable. You have a guy who has been doing fire protection. The fire protection people at the NRC were very resistant to any probabilistic method. So you look more carefully. They come from two places, Illinois Institute of Technology and Maryland, where they have fire protection programs. And they're all deterministic. If I have a room like this and there is a fire over there, how does the fire grow? What happens to the hot gases and so on? Very deterministic. And all of a sudden, PRA comes and says, well, no, we have to consider the probability of that fire, the probability of the gases spreading and igniting other targets and so on. And they were extremely reluctant to accept this approach. Okay? You often hear things like PRA is trying to predict what's going to happen. It doesn't predict anything. It's just bringing up to the attention of the managers what is already known by the community. Identifying the accident sequences, for example. And this, as I say, this information is not easily accessible without a PRA. Yeah. So, the first study, as I said, was done published in 1975. So what is the evolution of the NRC's regulations? The NRC staff was very willing in the 70s and 80s to take the results of the reactor safety study and other PRAs and impose new regulations. You know, oh, this vulnerability, okay, here is a regulation. In the 90s, though, there was a revolt from the industry. So wait a minute now, is that why we're doing the PRA, to spend more money and get more regulations? Because the PRAs now were done on a plant-specific basis. And they found that a lot of the regulatory requirements, which were expensive, did not contribute to safety. Now they had a method, a means of saying this particular thing is a waste of money. So the NRC changed this attitude with a lot of pressure from the US Senate. Regulators don't change easily. okay? Which means pressure from the industry, right? The senator is not going to stand up and say, do this, but the industry went to the Senate. So I'll tell you in a moment what the risk-informed approach is. In the 2000s until today, there have been quite a lot of risk-informed initiatives. Risk-informed initiatives are usually voluntary. In other words, it's up to the utility to decide to implement them or not. But the NRC also changed some of its rules. Rules are the law, which means everybody has to comply. But very few rules have been risk-informed. So in 1995, the NRC issued its policy statement, which tells the staff what the Commission would like to see, on PRA. So they say some interesting things. The Commission itself says that deterministic approaches to regulation, the design basis accidents in other words, consider a limited set of challenges to safety, as opposed to the PRA. A probabilistic approach considers a much broader set, the thousands of sequences I mentioned, and provides a logical means for prioritizing these challenges. The name of the game, guys, is prioritization. If you are a manager at a utility, at a nuclear power plant, there are all sorts of problems that come to you. You cannot treat all of them the same. They are not of the same significance to safety. That's a great advantage of PRA. You can prioritize in terms of risk. Typically, the prioritization is in terms of frequency. But at the NRC too, you don't treat everything as being of the same significance. You prioritize. So risk-informed. Finally, the Commission defined it. A risk-informed approach to regulatory decision-making is a philosophy where risk insights are considered together with other factors to establish requirements that better focus everybody's attention on design and operational issues commensurate with their importance to public health and safety. This is what we can do now with PRAs that we couldn't do before. We can quantify the risk. So this was a major change in the regulatory approach because the Commission says it's okay to consider risk. And here is what we mean by that. In the traditional deterministic conservative approach, the probabilities are not quantified. You rely a lot on the limited number of design basis accidents, but you implement defense in depth, and the downside is that you can impose what is called unnecessary regulatory burden. In a purely risk-based approach, your decisions would be based exclusively on the results of PRA, and we don't want that either. We quantified probabilities, we look at thousands of accident sequences. It's more realistic, but people will feel much better if we also have deterministic requirements and so on. So the risk-informed approach combines the two through a deliberative process. What does that mean? Regulatory decisions, and I think decisions in the industry too, are never based, important decisions, on just the results of a computer code or somebody's ideas. They're always the result of a deliberative process where a group of people, managers usually, get together and they consider a number of inputs. What are the options that we have? What decision are we supposed to make? Usually there is a technical analysis which is both the traditional deterministic analysis and the PRA, risk insights. But these are not the only inputs. You have to consider how good these are. What are the assumptions they are making? What are the uncertainties? What do stakeholder groups think about these things? A stakeholder group means that these are people who have an interest in the decision, but they are not decision makers. And we have the Union of Concerned Scientists, for example, Greenpeace, So these are input to the management. What decision criteria are we going to use? In the PRA space, we have the quantitative health objectives and the core damage frequency and so on. Are there any schedule constraints and maybe other factors? So these guys take all of this, debate, deliberate, and make a decision. Okay? And this is real life. Now, a new issue that has come up the last few years is the issue of multi-unit and adjacent sites. And Fukushima, by the way, we say Fukushima. The Japanese don't put an accent on a syllable, as I learned very quickly. It's Fukushima, without an accent. Fukushima, Hiroshima. But I still say Fukushima. So, Fukushima showed that, the interaction between units is very important. And strangely enough, PRAs were done for a single unit. So the question is now, why don't we do multi-unit PRAs? Well, the Commission here was very reluctant to ask the staff to do that. And one of the arguments is that currently we have few sites with 3 reactors, most of them have 2. But here's what's happening. Vogel, where they're building the new AP1000, will have 4. But then what's worse is you have these adjacent sites. So Salem 1 and 2 and Hope Creek are very close to each other in the sense that if there is one accident in one site, most likely that will affect the other site. And what makes it worse is that the sites belong to different utilities. Okay? So this is now something we don't like to talk about, but in my view, this may become important. But look at Canada. 8 units at the same site, and Kashiwazaki Kariwa in Japan, 7 units. So it's much. The NRC started a level 3 PRA several years ago that was supposed to address these two. It still has not been published, and I hear through the grapevine that not much progress has been made. Now we have the small modular reactors, and the NuScale Power submitted its design to the NRC a month or so ago for design certification, where you have a multi-module issue. This is an overview from above of the reactor. You have this pool here full of water, and you have the reactor modules, 6 on each side, if the utility wants, to come up with each module is 50 megawatt electric. So the total can be 600. This is a very different design from what we have licensed so far, right? You have all these modules close to each other. Each one has its own bay. So there will be all sorts of interesting questions that I think the NRC staff is going to come up with, and how to make decisions regarding safety of such a design. So this is similar to the multi-unit issue, but at a smaller scale. Now, there is a set of general design criteria in the books that were developed way back in the 70s. And general design criterion 5, this is the constitution, so to speak, okay? The design criteria of the constitution, the rules are the laws. Says that if you have 2 units or more in one site, important components and systems shall not be shared among nuclear power units unless it can be shown that such sharing will not significantly impair their ability to perform their function. The staff went to the Commission before my time and asked whether the safety goals should be applicable to the site or to each reactor separately. And the Commission said to each reactor, not the site. So almost all the PRAs in the United States are performed for single reactors. Now, internationally, after Fukushima, people started getting concerned about the multi-unit issue, and they're talking now about a whole site risk. As I said, the staff proposed it to the Commission, but said no. So in the United States, they are still interpreted on a per reactor year basis. But here is something that the NRC staff put in the standard review plan, that for small modular integral pressurized water reactor, like the new scale design I showed you, they want to see a risk assessment for a single reactor module. But if the applicant is seeking approval for multi-module plant, they want to see some assessment of risk from accidents that could affect multiple modules. In other words, the staff is acknowledging here that the technology for doing that is not here yet. But on the other hand, they cannot say it's okay. You really have to say something, and new scale is saying something. Now we come up to the latest. Even though nuclear power is at a low these days for economic reasons, there is an amazing amount of money that is being spent on advanced reactors. I've heard numbers like $1.2 billion. Okay? So the investors, these are not nuclear people. Bill Gates is funding TerraPower. The investors are asking, what is the situation in the nuclear business? And they are told that the NRC is a major player. So the guy is investing millions of dollars and says, so what may happen? And they tell him, after we finish the design, the NRC may say no. In other words, they have no indication from the NRC while they are spending their money that yes, the design is acceptable at this point, proceed to the next phase, and so on. And that creates a lot of unhappiness among the investors, even though, again, you have more than $1 billion invested. So, and the reason is the licensing process, that you have to have a complete design submitted to the NRC, and after an extensive review, they may say no. So if you have invested $800 million, goes out the window. Plus, of course, we have the problems with the traditional approach, the large break, loci, and so on. So there is a serious effort that started several years ago with a gas reactor first. Now it's for advanced reactors. And the leader in this effort is a utility, Southern Company. And the idea is not to define the design basis accidents arbitrarily, but using risk information. So they're saying, look, look at this plot. Here we have the frequency per plant year, not reactor year, for the whole site of accident sequences. And down here, it's the whole body dose at the exclusion boundary. And they say, this solid line here, there's nothing new there. It's already in the regulations. Okay? For very frequent events, for example, the regulations apply 50 millirem. No, I don't. I'll take it back. This line comes from the regulation. This line also comes from the regulations. So they say for a new design, you should do a PRA, develop the accident sequences, and have uncertainty on the frequency and the dose. As long as it's to the left of the line, then it's tolerable. Okay? And we can define now the design basis accidents using these accidents and applying a few more criteria that we don't have time to get into. So this is a much more rational approach. In fact, I'm reviewing the first white paper that they intend to submit in April to the staff. The staff is aware of this, but all they have said so far is that this approach seems to be reasonable. Reasonable doesn't mean anything in regulatory space. Of course, if they had said we don't like it, that would have been bad. But I understand their position too. I mean, they're saying we cannot really approve a major change in the licensing process without having an actual application. Okay? So there is hope that some sort of compromise will be achieved. Okay. A few words about Tokyo now and we'll be done. So this Nuclear Research Center was created a few years after Fukushima, and the stated mission is to assist nuclear operators and utilities to continually improve the safety of nuclear facilities. In other words, they don't want to just meet goals, which they don't have. They want continuous safety improvement. And the vision statement is to become an international center of excellence. There are about 110 people. I'm the head. I don't know what executive advisor means, but my friend Dick Mizer, former chairman of the NRC, is playing that role. We have a technical advisory committee consisting of 3 Americans, a Frenchman, and 2 Japanese that plays the role of the advisory committee on reactor safeguards, reviewing everything and issuing independent views. What is new for Japan is that the letters these guys write, we put up in the website. The Japanese approach was, we have to make a decision, we close the doors, we have the people in the room that are relevant decision makers, and we make a decision. Now, the letters from TAC, which are very often critical, are published. It's a desperate move to regain the trust of the Japanese people after Fukushima. And of course, there is always a response to the letter from the utility or from me. This is what we are doing to address your concerns. The acting head and the deputy heads take care of business when I'm not there. Something that we're very proud of, we formed a risk-informed decision-making promotion team, 10 people, 6 of which are former senior managers of the nuclear industry, to advise us as to how to proceed strategically and so on. And the rest is, I see a lot of these guys, CEOs and CNOs. And one of the recent, some of the recent activities, we issued a position paper for the proper roadmap actually for risk-informed decision making in Japan. We formed that promotion team, RIDM promotion team. We're about to issue a white paper on the history of risk-informed decision making in the United States and how Japan can benefit from it. We have advice to the utilities how to do HRA. And of course, in Japan, earthquakes, tsunamis, volcanoes are extremely important. So the PRA methods are still not very good. So we're having research projects there. And okay. I guess that's the end. All right, any questions?